Okay. Hello, everyone. My name is Xiaofu, and I'm one of the organizers of this event. We're very excited to see so many audiences are already here. So before we start, let me just run some logistics items with you. So basically, because this is a special online virtual seminar, so it might be a little bit difficult to directly interact with the speaker. So so if you have questions, you have several options. One is that if you fear that you would forget your questions, you could type your questions through the chat box, and we have 3 organizers monitoring the chat box, and we would forward your questions at some short breaks or some proper points. And also you could hold your questions until the end. We will have approximately 10 minutes Q&A session. So you could also ask it by yourself in the end. So that's it. That's the logistic issue. And today is our 5th talk, and today our speaker is Professor Nikos Sidiropoulos at the University of Virginia. Perhaps many of you have already known Professor Sidiropoulos' work pretty well, especially if you work with tensors or if you work with wireless communications. But anyway, let me still take the honor to briefly introduce you our speaker. Nikos Sidiropoulos earned his PhD degree in electrical engineering from the University of Maryland, College Park in 1992. He has served on the faculty of the University of Virginia, University of Minnesota, Twin Cities, and the Technical University of Crete, Hania, in Greece. For some of them, he served twice. He is now serving as the department chair of the ECE department at University of Virginia, Charlottesville. Professor Sidiropoulos' research interests are in signal processing, communications, optimization, tensor decomposition, and notably in recent years, very heavily in machine learning and data science. So I was very fortunate to work with him on a lot of these data science topics in recent years. Professor Sidiropoulos has won a lot of prestigious awards. He received the NSF Career Award in 1998 in the first semester of his faculty career, if I remember correctly. He has also won the IEEE Signal Processing Society Best Paper Award 3 times. In 2001, 2007, and 2011, respectively. He was also an awardee of the 2013 Distinguished Alumni Award from the University of Maryland, Department of ECE. Professor Sidiropoulos has been very active in our community, offering his service and leadership. He served as IEEE SPS Distinguished Lecturer, and served as the vice president for membership of our society. He received the 2010 IEEE Signal Processing Society Meritorious Service Award. He's a fellow of IEEE and also a fellow of EuroSIP. So without further ado, I'll pass the microphone to Professor Sidiropoulos. Nikos, the floor is yours.
Thank you very much, Xiao. I'm humbled. It's really good to be with many good friends and colleagues to talk about one of the things that I'm passionate about, which is work at the confluence of tensors on one hand and probability on the other, with a good dose of signal processing and Fourier series and Fourier transforms, as you will see today. So this is joint work with my students, Magda Amiridi and Nikos Kargas, who are pictured here on the left. And it's about multivariate density estimation using a low-rank characteristic tensor approach. So I thought I would take this opportunity to remind some of you who have been at UVA and others who haven't seen UVA, how UVA looks like. So this is a picture of the main campus, the mall with a rotunda. UVA was designed by Thomas Jefferson, and this is the centerpiece of the university. It's in a beautiful area overlooking the Blue Ridge Mountains, as you can see. And if you can see my mouse, my pointer, on this side of the lawn, as it is called, is a building that has an interesting facade, since three of the authors of this work are Greeks. And the facade says, in Greek, «Και γνώσεστε την αλήθειαν και η αλήθεια ελευθερώσει ημάς», and you shall know the truth, and the truth shall make you free, shall set you free. So this is quite inspiring for us. So I will be talking about density estimation, in particular modeling and estimation of high-dimensional probability densities. And this is an unsupervised learning task that is important in a number of applications. I will give you examples next. So the basic goal is shown here at the bottom of this page. You are given, in the one-dimensional case, there is some data generating distribution, which is a one-dimensional bimodal PDF, as shown here with a blue line. And you are provided points on the x-axis. These are these blue circles at the bottom. And these points are drawn in an IID fashion from this PDF. And naturally, you will have a higher concentration of points down here, right? Where the mode is of the distribution. And again, here, where there's another smaller mode of the distribution. So you are given these data points, and your goal is to estimate the data generating probability density, right? So that's the one-dimensional problem here. We will be talking about the high-dimensional extension of this problem. And by high-dimensional, I mean from hundreds of random variables to thousands, to many thousands, or possibly even more random variables, right? So another example to see this, so we have images here on the right, which are drawn from some data generating distribution, which happens to generate images of dogs and rolled towels, which kind of look alike. And given examples from this training data, you would like to learn what is the underlying distribution, the data generating distribution. So this is our goal. And it is an important problem in the broad area of unsupervised machine learning, right? So the more general problem that we will be talking about is the following. You are given a data set. It contains M training vectors. Each one of the vectors is in Rn, and n can be very high dimensional. You assume that these data are drawn from some unknown data generating distribution. You don't know the distribution. You are given the data samples, and you are scratching your head, and you're asking, okay, so what is the data generating distribution? Can I learn the data generating distribution? And if you are like me, of course, the first question you will ask is why? Why do I bother to do that, right? And the answer is, if you know this data generating distribution, you can address a lot of problems in machine learning, right? For example, if you know the joint distribution, you can estimate, right? Or you can compute conditional distributions. And conditional distributions, let's say, of some variables, a subset of variables, given another subset of variables. That is important because it allows you to impute or predict or estimate missing variables from available variables, right? So this is important. You can also, if you know, of course, the joint distribution, you can derive optimal estimators and optimal classifiers. So you can do optimal statistical inference, right? Furthermore, if you know the distribution, you can synthesize synthetic data, right? So you can sample from the distribution and generate images that look like, right, dogs or towels, right, or whatever it is that you are trying to synthesize, right? So these are the important reasons why we're interested in high dimensional density estimation. All right. The problem is a challenging one, and there are many challenges here, the most important being the case of dimensionality, right? So we are typically, so images are, 256 by 256 or, even higher resolution. So modern data sets that we're working with are very high dimensional, they're complex. And in fact, the number of examples that we typically have is relatively small, right? We talk about big data, but if you have very high N, you really need very, very high M, right? To be able to learn a meaningful approximation of the underlying density, right? So the case of dimensionality is an important challenge, perhaps the most important challenge that we will tackle today, at least to some extent, as you will see. Another is you might observe incomplete realizations. So you might not be given the complete vector x1, but only, let's say, a punctured version of x1, in which maybe 70% of the elements are missing randomly or systematically, right? Systematically, of course, you cannot do anything about if they are always missing, right? But in practice, you may be given vectors with elements, maybe a large percentage of elements that are randomly missing. And you still wish to learn the joint distribution. There are important questions here. If you are a statistical signal processing guy, you have a pedigree in this area, there are important questions about model identifiability, about the expressivity tractability trade-off, meaning that you wish to have a model that can express a large class of distributions. At the same time, that model has to be tractable, has to be parsimonious so that you can estimate the parameters. And of course, there are questions of sample complexity. So it's a big problem area with a lot of important questions. Just to motivate a little bit more applications of high dimensional density estimation, one of the important applications is to basically be able to predict relatively rare events. So for example, when you train automatic driving, let's say, algorithms, most of the data that you train with are kind of mundane data, but you are interested in actually learning how to behave, right, in rare events or events where, one has to be careful. For example, when there are pedestrians crossing the street, or when there is an accident, right? So these are sort of outlier events. So density models are useful there. You may be interested in creating realistic artwork. That is learning to sample from an underlying distribution, which is very high dimensional, or creating, artificial faces. Examples that have become increasingly popular in recent years in the machine learning community. Closer to our signal processing home, you might be interested in, for example, language translation. If you learn a model of the conditional, let's say, conditional probability between English and Chinese, you might be able to use that model to generate a translation of an English sentence from a Chinese sentence or vice versa. You all notice how when you type on your cell phone or your email, it automatically recommends the next word. And how does this work? It is basically a probabilistic model that is built given the previous words. Here, the previous words are, when is a good time to buy a? And you might get suggestions for completion, a house, a home, a car, and so on and so forth, right? So all these auto-completion things work based on conditional probability. And basically, if you have a joint probability model, you can figure out the conditional probability model. And finally, again, closer to signal processing and language modeling, if you have a joint model of speech and language, then you can infer spoken words from audio signals, or you can synthesize audio signals from text, right? So the applications of density estimation, in particular higher dimensional density estimation, are enormous. All right, so let me now tell you about the starting point of this talk. So a few years ago, together with my student Nikos and my postdoc at the time and good collaborator Xiaofu, we worked on the categorical case. So the starting point is this. If you have categorical random variables, meaning that every random variable assumes a value in a finite alphabet, right? Which may be numerical or it may not be. For example, a fruit can be an apple, a banana, or an orange, right? It's a categorical variable. If you are looking at the joint probability mass function, right, of a number, any number of categorical random variables, that joint probability mass function is a tensor. And what we have shown in our work, in this paper, which was published in TSP a couple of years ago, what we have shown in our work is that every joint PMF in the face of Earth of a finite alphabet random vector can be represented by a naive Bayes model. And what is a naive Bayes model? A naive Bayes model is a probability model, a graphical model, which has one hidden random variable, one latent random variable, and all the other random variables are sort of hanging as leaves under this hidden random variable. And given the hidden random variable, the other random variables become conditionally independent. If you are given the value of the hidden variable, the other variables are conditionally independent. That seems to be a very restrictive model. What we have shown in our work, it's called a naive Bayes model. We have shown in our work that it is not naive at all. Every joint PMF can be represented by this model, provided that you have a high enough number of latent states, which is tensor rank in this case. We have further shown that if that tensor has low rank, then very interestingly, the high dimensional joint PMF is identifiable almost surely, right, from three-dimensional, very low order, marginal PMFs of triples of variables under low rank conditions. And this has a very interesting connection to the Kolmogorov extension theorem, because essentially what Kolmogorov said was, if you have a stochastic process, infinitely many random variables, right? If you have a consistent recipe, right, to specify any finite dimensional distribution, then there is a unique measure for the entire process, right? What we are saying here is that under certain conditions on the rank, right, in fact, you don't need to specify any finite subcollection. Specifying actually a subset of third order marginals is enough. Okay, so this is the starting point of today's talk. And what we wanted to do after that is to extend this approach to continuous random vectors. But there is a basic problem here. The problem is that whereas the joint PMF is naturally a tensor, the joint PDF, when the arguments here take values in R, is not a tensor. It is a multivariate function, but it's not a tensor. So the question is, can we still use tensor tools? And if you are an engineer, of course, the first thing that comes to mind is discretization, right? So let me quantize each one of the random variables to a finite number of bins. Then I will make this thing a tensor, and I will be able to proceed. But this has a number of drawbacks. It works, actually, reasonably well, but it has a number of drawbacks, right? The first is, well, do you do coarse quantization or fine quantization, right? In one case, you have coarse quantization, then you have discretization error, right? If you make fine quantization, your statistical accuracy is not going to be something to write home about, because in any bin, you will not have enough data to average, right? So there is a clear trade-off here. There is a more general question: how do you choose the quantization scheme, right? Furthermore, in general, there is loss of identifiability, because even if you are able to estimate the multidimensional histogram, right, you are generally not able to go back and estimate the underlying probability density function. So that is a problem that we'd like to avoid, right? So can we avoid that? That is an important question. As we will show in this talk, in fact, we can, and we can view tensors as universal PDF approximators, as we will see. We will see actually that if we assume that we have a probability density function that has compact support over a hypercube in high dimensional space, and it is continuously differentiable up to certain order p, right? Then based on these assumptions, it can be shown that this distribution can be approximately modeled using a finite mixture model in the Fourier domain. And assuming that the Fourier domain specification is low rank, then in fact you can have a controllable approximation of the multivariate density that is identifiable. In fact, we will show that high dimensional joint PDF recovery is possible even if you only observe subsets of the random variables and not the entire random vector, if you observe triples of random variables, and in fact, not all triples. Okay, so how does this go? Let me tell you a few things very quickly about tensors. Because time is limited, I will not spend much time here. So what is an n-way tensor? It is basically an array indexed by n indices. In this particular illustration, an array indexed by 3 indices, I, j, k. A matrix is a two-way tensor, which is indexed by 2 indices, I and j. Very similar to matrices, any tensor can be decomposed as a sum of rank 1 tensors. For matrices, a rank 1 matrix is the outer product of 2 vectors. For tensors, a rank 1 tensor shown here is the outer product of 3 vectors, which means that every element of that tensor, right, is the product of an element of A1, an element of A2, and an element of A3 vectors, right? So that's an outer product. The rank of a tensor is the smallest number of such chicken fit rank 1 tensors that we need in order to synthesize the given tensor. Now, this rank decomposition for matrices, of course, you know it very well. It is, you know about SVD. For tensors, it has a very fortunate property. And the property is that for tensors, low rank decomposition is unique under relatively mild conditions, which means in simple words that if you give me the tensor phi, in principle, and if the tensor phi is low rank, and what low rank means is practically not full rank, but low rank for tensors can be actually very, very high, especially for very high dimensional tensors, right? If you give me phi and phi is low rank, then I can actually put my hands and recover the rank 1 factors of this tensor in a unique way because exactly of uniqueness. Now that's computationally a hard problem, but we have good approximation algorithms to do it. So I will not spend too much time again talking about tensors. In fact, I will skip the slides in the spirit of parsimony. All I'd like to say is that there is a lot of work, 50 years of research on when tensor decomposition is unique. I have also worked a lot in this area. In recent years, algebraic geometry fellows have provided some really nice results, including Ciantini Notaviani, but I will skip that because that's not very important, let's say, to go into the details here, right? Let me now go back to my starting point, which is multivariate density estimation. And let me tell you a little bit about what we know about this classical problem. It's a classical problem, although no one has really tackled it in the very high dimensional case, which is what we do here. So classical density estimation comes in 2 main genres. One is parametric models, which generally make strong assumptions about the structure of the data generating distribution. If these assumptions hold, they are very good. If not, they are fragile to model mismatch. The classical example here is a Gaussian mixture model, right? Which is broadly used in many applications. It comes with computational and estimation theoretic challenges in the high dimensional case. The other main genre is non-parametric models, which basically make mild, what I would call universal prior assumptions, for example, smoothness. And again, there are many techniques in this area. Kernel density estimation, high order histograms is one approach. It becomes computationally intractable for large M and N. And using orthogonal series density estimation is another. Our work falls under this category of orthogonal series density estimation. And the basic idea in this category is that you approximate a PDF using a truncated sum of orthonormal basis functions. And this is well known. It has been studied for many years. But it also suffers from this very, very important problem, which is the curse of dimensionality. If you have 1,000 random variables to model, the joint PDF of 1,000 random variables, then you need, constant to the power 1,000 coefficients, which is out of this world. So you cannot do it. All right. What about modern methods? I'm not sure if you, how many of you are familiar with this, but in recent years, there's been a lot of work on density estimation using neural network kind of approaches. And so there are, again, two classes. One is explicit density estimation using so-called autoregressive neural models. And these are models that build upon essentially conditioning. So they write the joint distribution as a product of conditional distributions, and they use a neural network to model that product. And these are several examples of these methods. These are primarily meant for point-wise density evaluation, meaning the goal of these methods is to have a neural network where you input an input vector X, and the output of that neural network, right, the final output is an estimate of the PDF at point X. All right. So this is sort of the main raison d'etre of these approaches. They have limitations. There are no identifiability guarantees. They cannot predict more than one or two missing elements in the input. And they are more or less black box approaches with a lot of leaps of faith, let's say. The other general class is implicit density estimation. And this includes things like variational autoencoders and Gaussian adversarial networks. These are mainly used for artificial sample generation, right? So you're not explicitly modeling the joint PDF, but you learn how to sample from it, basically. All right. So what is our goal here? Our goal is to come up with a method for high dimensional density estimation that is non-parametric, that is expressive, flexible enough to represent a wide class of distributions, which is tractable and scalable to very high N, both computationally and memory-wise, which has some theory and principle behind it. It's not completely black box. And of course, ideally, or perhaps the most significant thing you want is that it is an accurate model of the underlying, it gives you accurate modeling of the underlying PDF. Okay, so towards this end, let me remind you of a few basic facts from probability theory, which will prove useful for today's discussion, right? So let us look at the one-dimensional case. You have a real valued random variable X. You know that the characteristic function of this random variable X is the Fourier transform of its probability density function. So phi X of mu is the frequency variable, let's say, is the Fourier transform up to a sign here, Fourier transform of its probability density function, which from the fundamental theorem of expectation can be interpreted as the expected value of a function of the random variable X, which function exponential to the J nu X, right? So this is from the fundamental theorem of expectation. And then you have the inverse Fourier transform. You can invert the characteristic function and get back the original PDF, right? Now, one point to note is that if you are interested in estimating the characteristic function, you don't need the PDF. You don't need the PDF because of this expectation interpretation you can use sample averaging of the exponential to the j nu x1, right? x2, x3, x4, etc. You can use sample averages to estimate this directly as the sample average. You don't need the PDF. All right. Now, we can go to the characteristic function domain, but that doesn't seem to buy us anything, right? Because that's an infinite dimensional function that we are trying to estimate here, the PDF. And if you go to the characteristic function domain, it's actually a complex infinite dimensional function. So that doesn't seem to buy you much. Okay, so let's make it a little bit better, right? Let us assume that the PDF of X is compactly supported on the interval 0, 1. In fact, compactly supported on any interval. If you know the interval, you can map it to 0, 1, right? You can scale the random variable and shift it down to 0, 1 so that it is without loss of generality. If that happens, then the PDF can be thought of as one period of a periodic function and then represented by Fourier series, whose coefficients can be viewed as essentially samples of the characteristic function. So what have we won by virtue of compact support? Going from an uncountable parametrization to a countable parametrization, right? Because we only need the Fourier series coefficients. So that's what we gained by assuming compactness of support. Furthermore, if you assume that this density is continuously differentiable up to order P, then we know that the magnitude of the characteristic function, right, decays like 1 over 1 plus k to the p, which together with Parseval's theorem implies that if you truncate the series, right, you have controllable error and you can quantify the error, right? So you can estimate the series coefficients through sample averaging. You can truncate the Fourier series, and that leads to controllable error, which you control through the parameter k, the smoothing parameter k for the truncation. Now, I'm not sure how many of you have imagined this before. I hadn't up until a couple of years ago when I first thought about this. But you know, you might wonder how well can this work. So here is how well this works, right? So this is an example of a one-dimensional mixture of two Gaussians. The blue curve is a mixture of two Gaussians, right? On the left, I have the magnitude of the Fourier transform of the blue curve, which of course decays, right? Because the blue curve is smooth, right? And I saw in red dashed line here, right, what you get if you only reconstruct the density using 9 Fourier series coefficients. So you see that with only 9, k equals 4 in this case, right? So from minus k to k, 9 Fourier series coefficients, you get this approximation of this density, which is pretty remarkable, right? So actually, there is a lot of reason to estimate things in the characteristic function domain, because there you can reuse all the samples, all the training samples that are given to you to estimate every coefficient and then invert, and then you get actually a very good approximation. All right. Now, thanks to Joseph Fourier and several others who worked in this area, of course, everything carries over to the multivariate case, even if you have 1,000 random variables or more, right? So if you're given a random vector, you can define the joint or multivariate characteristic function, and it is a multidimensional Fourier transform, and it can be estimated directly through sample averages, and it can be inverted. That is not very interesting because this is, of course, suffers from many deficiencies or problems. One is that it is an uncountable parametrization and it suffers from the curse of dimensionality. So let us sort of break it down again as we did in the one-dimensional case. So assuming that the multivariate PDF is supported in the hypercube, is compactly supported, I can always map it in the hypercube. Again, I can represent it by a Fourier series, so translate this to a countable parametrization. In fact, if it is continuously differentiable up to order P, I know results about the decay of the Fourier series coefficients, and I can bound the approximation error, and I can control it by the smoothing coefficient K. So I can now truncate the Fourier series And when I truncate the Fourier series, what do I get? I get a tensor, a characteristic tensor, right? In n way, in an n way characteristic tensor, where n is the number of random variables that I have. Okay, but I still have a problem. And the problem is that the number of parameters in this parametrization, right? So I will have now a characteristic tensor, right? Whose indices are now frequency variables, basically. But the problem is that if I truncate every Fourier series to k coefficients, let's say, right, then the number of coefficients that I need is order of k to the power n. And if n is even 100, it's a lost game, right? So I cannot proceed. Except, and this is the key point of our approach, the other key point of our approach, if I assume, if there is reason to think that this Fourier tensor, this characteristic function tensor, right, can be approximated by low rank. If I introduce a low rank parametrization of this tensor, then in fact, I can control, right, the model complexity. I can control the number of parameters. And in fact, I can bring it from exponential, right, to something that is linear in the number of variables that I have. And this is key. For this thing to work, for any approximation of this kind to work, I need to have, right, a number of parameters that does not grow exponentially with the number of variables. And the only thing you can do that is by low rank approximation with what is actually very low rank. And we will see that it works extremely well in practice. Now, this has, in addition to circumventing the curse of dimensionality, which is the key problem in very high dimensional density estimation, the key problem is curse of dimensionality. In addition to circumventing that, you get a side benefit, which you further denoise the naive sample average estimates of the characteristic function points. All right. Now, if you do this, and if you assume this model, the beautiful properties of the Fourier transformation, right, bilinearity and separability of the multidimensional Fourier transform, actually you can pull this hidden variable out, and you can push the Fourier transformation inside, right? And the Fourier transformation, the multivariate, think about it this way. If you have an image, a rank 1 image, and you take the Fourier transform, the 2D Fourier transform of a rank 1 image, that is given by two one-dimensional Fourier transforms. So because of rank decomposition, in fact, I don't even need the multidimensional Fourier transform. I only need the one-dimensional Fourier transform and the low rank property, and I'm done. So effectively, I get a model of this kind. And in fact, we have proven the following result. Truncating the multidimensional Fourier series of any compactly supported random vector is equivalent to approximating the corresponding multivariate density function by a finite mixture of separable densities. And what are these separable densities? The inverse Fourier transforms of this rank 1 characteristic functions, right? So this model is particularly simple. The final model is very simple. It is easy to draw samples from. It is very easy to marginalize, because if I integrate here with respect to one variable, right, the integration comes in and picks the marginal, the conditional marginal distribution, integrates it out, and it simply drops from this product, right? So it allows easy marginalization, it allows easy computation of conditional densities and prediction imputation. So that's a particularly fortuitous model. Now, you know, if you are like me, your question should be, does it work? Yes, it does. Let me show you an example, even a two-dimensional case. So here is an example. Look at the bottom row here. What we have is the 2 half moons distribution, right? So we have 2,000 points drawn from this 2 half moons distribution. In this figure, the number of Fourier series coefficients is set to 11, right? So I have, in fact, 23 coefficients minus 11 to 11, including 0, right? 23 Fourier series coefficients for each one of the two random variables. And I'm showing you how well the method works with rank 2, 4, 6, 8, and 10. And you see that with rank as low as 10, right, you get a very good approximation, right, of the two half moons distribution, and same for the circles distribution, right? And if you want to have, let's say, even better definition, you can actually use a higher K and or more training samples. So this thing works. This is an artificial data set, but let me show you a real data set. Again, the bottom row here. Here, this is a height on the x-axis versus weight. This is real data, right? People's height versus weight. This distribution, this is a two-dimensional PDF. It is very highly correlated, of course, because weight is highly correlated with height. It is actually a mixture of two Gaussians, one for women and one for men, with a strong overlap because there are a lot of men and women that have similar height weight profiles, right? But there are two Gaussian distributions here. This is actually a full rank distribution, right? It's actually close to a ridge, right? But look how well you can approximate it with rank 8, right? So the take-home point here is this. In real life, no distribution is low rank. And no distribution can be perfectly modeled using a finite Fourier series. But almost every distribution that we have seen can be very well approximated with low rank. And this is a real example of why this happens, right? So low rank is a really good model for joint distributions and very high dimensional joint distributions, as we will see today. I will spare you this. How about the proposed approach? What does it boil down to? It boils down to relatively simple steps. The first step is you estimate the characteristic tensor. Actually, we don't need this step. You can skip it. But conceptually, let's think about it this way. You estimate the characteristic tensor. This estimate is done by means of sample averages of this kind, right? Very simple. Important to note that all the data affect each and every Fourier series coefficient, right? So each coefficient can be computed from all the data. Contrast this to histogram estimation. If there is an area in the histogram where probability is very low, you will get no samples there, and therefore you will have high variance. Here you are using all data points for all coefficients that you're estimating, which is a good thing. So you take this tensor, you fit a low-rank model, you invert it using one-dimensional Fourier inversion, which is done through the FFT, right? And then you have the conditional densities and you have your overall model, right? There are a few things you have to be careful about. I will not spend your time on the details. You can read them up if you want. And I will be happy to share my slides. But the way what I would like to stress here is that we actually don't compute in practice the full characteristic tensor. And we don't fit the full model. And the reason is that computing the characteristic tensor, right, from a computational and from a memory point of view already has exponential complexity in the number of random variables. To avoid that, we use our special Kolmogorov trick, let's say, which says that for low enough ranks, right, you can in fact fit third order characteristic functions. You can actually estimate and fit third order characteristic functions, and from them do a coupled decomposition and synthesize the full PDF. So in fact, we only estimate, decompose jointly, right, fit jointly third order characteristic functions. From them, we are able to reconstruct the full high order characteristic function if we want, or simply invert directly and get the joint density. This has important advantages, significant computational memory, right? We avoid the curse of dimensionality. It also allows us to work with incomplete vectors. So you give me vectors x1, x2 to xn, each one of them may have, 90% of the elements missing. I can still work with this, right? So that's an important thing. Again, the algorithm per se is not very important. It's a coupled tensor factorization under some special constraints, which have to do with the properties of the characteristic function. I will skip the details. It's a complex decomposition because you are in the Fourier domain. I will skip the details, though, for lack of time. And here I come to performance evaluation. Because at the end of the day, you know, you can have all the theory you want. And this is something that we see often nowadays in machine learning venues. There is this beautiful theory about global optimality and guaranteed this and guaranteed that, but no accompanying experiments to validate and corroborate that this thing works in practice. I'm an engineer and I'd like to make sure that the thing works in practice before I sell it. So this is what we did here with Nico and Magda. So Magda did a lot of work here with Nico. Performance evaluation using real data sets, high-dimensional data sets from the University of California, Irvine repository. We're using 3 performance measures. One is the average log likelihood of unseen data samples. So this is commonly used in the machine learning literature. The other one is mean absolute error performance or mean squared error performance you can use if you want on regression tasks where we are trying to predict, we are hiding certain variables systematically, right, from all the data set, right? We're hiding the random variables and we're trying to predict hidden random variables, right? So regression tasks, the important performance metric there is mean absolute error or mean squared error. And we will also show you image sampling results. As I said earlier, our model is a data generating model where we can very easily sample from it. So we can generate synthetic images and I will show results. So for our experiments, we use 10 Monte Carlo simulations. We average out results over Monte Carlo simulations. We split data, 80% training, 20% testing. And to pick parameters, we use cross-validation on the 5-fold cross-validation on the training set. We only have 2 parameters, right? So most methods that you will find in this area, right, have zillions of parameters and require fine-tuning. We only have 2. One is the smoothing parameter, the truncation parameter in the Fourier series domain, K, and the other one is the tensor rank parameter, F. And we pick them through cross-validation from a small range of parameters. We are using several baselines for comparison, 2 from the classic literature, Gaussian mixture models and kernel density estimation, and 2 from the state-of-the-art neural network literature in recent years, namely RNAID and MAF, which are state-of-the-art density evaluation methods, right? So here's the first screen of results using average log likelihood on unseen on the testing data samples, which is the 20% that we put aside for testing. And what you see here is a number of data sets. Let me go over the data sets. Some of them are fairly low dimensional, red wine, white wine, 11 dimensional. That is still a very high order tensor. This theorem proving 51 dimensional, superconductivity 81 dimensional, gas sensor array drift 128 dimensional. We have more recent results with order of 1,000 random variables that we can handle using another variation of the method. So we can go to very high numbers of variables. Now, let us look at the results. So by the way, N is the dimensionality, M is the number of training samples. So that you see that we are, the number of training examples here is relatively small, right? At least in several of these cases. So for method, mixture of Gaussians, MOG, kernel density estimation, RNAID and MAF are the 2 neural state-of-the-art methods. Low rank characteristic function density estimation is our method on the right. What you see highlighted in boldface is the winning method. For red wine, we win considerably, right? For white wine, the same. These are the 2 smaller data sets. The difference is big, especially, for example, relative to things like MOG or KDE, right? So 11.9 to 16, but even relative to neural networks, 15.2 log likelihood versus 16.4. But for some of the bigger data sets, like for example, PCB, printed circuit board, right? Gaussians 152, KD 147, the neural methods 170 something, we do 194, which is significantly higher. Superconductivity, again, higher, right? In all cases where we are not the strict winners, and I think there is one case here where we are beaten. Yes, so the Corel images, RNA gets 223.6, we get 222.6. So that's a small difference here, right? So we're either the best method with significant difference or very, very close to the best method in terms of this metric. In terms of regression, prediction, imputation, whichever way you want to call it, the metric is mean absolute error, which what we're using here, and the smaller the better now, right? What we're using to estimate the output given the density estimate is conditional expectation. So assuming that our density estimate is correct, we are using the Cadillac here, the best possible thing that you can do from a mean squared error perspective, but we're actually reporting mean absolute error. Mean squared error, we're doing slightly better, in fact. So again, 1.28 for mixture of Gaussians, the best neural network 0.63, we do 0.56. PCB, the best neural network 4 point something, we do 3.85. Superconductivity 16 point something, we also do 16 point something. We actually lose a little bit relative to R8 in this one. So again, very good results. Now we can easily impute more than one random variables. The neural network methods have a hard time doing that because they have to do enumeration over essentially a multidimensional grid search. And they don't do very well. Actually, we're doing much better in predicting more than one missing random variables. And I promised an image example, and here is one. So what you see here is real digits from the USPS data set. And these are actually synthetic digits, right? Randomly drawn from our density estimate, right? For each one of the classes, for a rank as low as 8. Now, these are n is 256. So we're talking here, guys, of a 256 order tensor. We are learning a 256 order tensor, which can have rank that is absolutely huge. We are limiting its rank to f equals 8, right? And 15 Fourier series coefficients per dimension, right? And this is how well we learn, right? With rank 8. Clearly, they are not perfect digits, right? But it is really good relative to other baselines in the literature, and it shows you that indeed with very low ranks, you learn. All right, so time to recap and take questions if you have. So I talked about non-parametric multivariate density estimation. Our approach is based on going through an orthogonal series decomposition, and as sort of testament to our, to the founder of signal processing, arguably Joseph Fourier, right? We're using the characteristic function approach. And the key idea here is that we're using the characteristic function. We are truncating the Fourier series, right, in the characteristic function domain, which is allowed because of smoothness, right? We're truncating the characteristic Fourier series, and then we are imposing low-rank structure on the complex characteristic tensor. And what is surprising is that very low ranks as low as 8, right, can do actually a very good job in learning the density and predicting likelihood, predicting missing variables for many real data sets. In the process, we showed that any compactly supported density can be approximated by a finite characteristic tensor whose size depends on the smoothness of the density. And we showed that what you can do under certain conditions, assuming exact low rank in the Fourier domain, is you can learn the true data generating distribution, or actually a controlled approximation of the true data generating distribution. So with that, I would like to conclude my talk. Thank you, and take any questions that you may have.
Hi, Nikos. So thanks very much for the really great talk. So actually, there's quite a lot of questions. So let me start with the first one, maybe. The first one who typed into the chat box. So Irene asked, can the method be used to estimate the joint density of circular, and circular linear random variables? And also, how tolerable is the method to outliers?
Yes, so the method can be used to learn any density under the assumption that the density is sufficiently differentiable, basically, right? The only thing we are using, compactly supported, right? We are using two fundamental assumptions: compactness of support, which is in practice, we model things as Gaussian, but there is nothing that is really Gaussian, right? That has an infinite tail. So compactness of support is one, and continuous differentiability, smoothness is the other. So long as these are satisfied, in theory, the method should work, right? And practical experiments. Now, regarding outliers, we haven't explicitly modeled outliers, but we can do that. But we haven't done it so far.
But I guess the question is about how sensitive it is to the outliers. So like the tolerabilities. So how is it from experiment, for instance?
Yeah. So we didn't actually, the way to test this is actually insert outliers to some real data set and see how sensitive the method is, at least on the experimentally, right? So we haven't done that. So I cannot answer this question.
Okay.
But I believe that because outliers will typically, let's say, be few, right? If you do low rank modeling, right, you will be forced to model the part of the distribution, right, that is more important, let's say, in the characteristic function domain. So my intuition is that it will be pretty robust with respect to outliers, but I haven't tried it.
Okay, sounds good. So there's also an interesting question on, like, why do you consider working in OSDE rather than KDE? So it's a question from Addie. So she's wondering, like, what are the general benefits of OSDE over KDE?
So we're not using any orthogonal series, right? Although in principle we could, right? We're using Fourier series. The answer is kernel density estimation. I mean, one could work with kernel densities, right? And we actually showed examples, right, comparing with kernel density estimation. It doesn't do as well. I think the reason is the moment you assume a particular kernel, right, you are assuming a certain family of densities that you can model with that kernel. Right. When you assume a Fourier, I mean, every distribution, has this characteristic function, right? And every distribution that is smooth can be approximated with a truncated characteristic function. So I think the reason is that the model we're using is more general. It makes fewer, assuming that you have smoothness, it makes fewer assumptions. And of course, so that's sort of my thinking.
Okay.
Clearly, you can use multiple. Clearly, you can use multiple kernels, right?
You can use multiple kernels, but again, I mean, you are taking one class of functions and you are taking the union, let's say, of two classes of functions. But it's one of the nice, but the complexity will be high, right? Because the training examples come into the complexity calculation, right? Whereas what we do is a very simple approach, right? Because the complexity is controlled by one parameter, the rank.
Can I ask?
That's interesting. So let's move on to the next question, I guess. So here's a question from Yanis about how do we test the approximation accuracy? So what kind of metric do you use to test how accurate your approximation is?
In real life experiments or in controlled experiments, of course, if I create the PDF, I can test accuracy, right?
Okay, yeah.
In real life experiments, you don't know the PDF, so you cannot explicitly test for accuracy. But the log likelihood metric, right, this is what it measures, right? KL divergence, essentially, right?
I see.
So the log likelihood metric measures KL divergence, right? So that's why we are reporting that. It's an estimate, right? And of course, ultimately, if you are interested in prediction, mean absolute error, mean squared error, that's the bottom line, right? So the best method is the method that gives you the least error in experiments.
I see. And so I think the next question is from Joachim. So maybe he can speak up. Can you?
Joachim, please.
Yeah, it's very late in his time, I imagine.
It's very early. It's 3 o'clock in the morning, but it was definitely worth it. It was an excellent talk. I always enjoy your talks.
Thank you, Joachim.
So I guess the background is that I was forced into a privacy project at one point, and I've been thinking a lot about data disclosures. And so the question is, can you characterize how much of the information from individual samples that are contained in the PDF low rank representation? So can you actually use it as a data aggregator for high spaces? Yeah,
so you're bringing up an interesting point, if I understand correctly, Joachim, and I thought about that, but I haven't stressed it. Yes, so you what you are saying is that the characteristic tensor incorporates of course, has all the information to get the joint PDF, but it is in aggregate form, and you don't have the individual X samples, right? Is this what you're saying?
That's what you would like to have if you wanted to anonymize the data. The question is, does that work?
So yes. So indeed, of course, any density estimate, right? If you use the data to estimate the density, right, and you throw away the data, then yeah, I'm not an expert here, so I will not I will not try to pretend I am. I think it is interesting to think of the characteristic function domain as aggregating the data in a way that preserves privacy, but yeah, I need to think more about this. I need to think more about this. I saw you had another question.
Yeah, no, that was more of a minor thing. So when you did the digits, you chose the rank 8. Why not 10? It seems like 10 would be more natural for 10 digits.
Yes, this particular example, so what I was modeling was actually the class distributions. So the 0 distribution, the 1 distribution, etc. In general, yes. So if you model, actually rank 10 is not enough to model all the digits. You need rank 30. You need rank 30, but rank 30 is extremely small for a 256 dimensional space, even of binary things, right? Because if you have 256 random variables that are binary, the maximal rank is 2 to the 255. And we're using rank 30, which is ridiculously small. And if you want, one take-home point from this is, before our work with Nico and with Magda, nobody had ever thought of using tensors of order hundreds and thousands, right? And nobody had ever thought of, I had a hard time believing in the beginning that you can take a 256 dimensional tensor, right? Real tensor, right? Real PDF of real data. And rank 30 is good enough to predict better than any other method. Yeah. So this is sort of the what I find remarkable from a practical point of view. Very low ranks are enough, and the basic intuition is similar to taking your picture and taking the first 5 singular components, singular vectors, and approximating your picture with 10 singular, 10 principal components. You can still recognize it is Joachim, and the same thing is happening here, basically, right? The fundamental elements of the distribution are captured by these low rank factors.
All right, thanks.
Okay, so thanks. So actually, let's follow up with maybe the last question. So there's actually another question from Irene. So she's asking about like, to what extent can we also tolerate missing data? So we talk about outliers, we talk about noisy data, but what about missing data?
Thank you for this question. The answer is to a great extent. Each one of those vectors, take the digits, right? Take a picture of digits. Hide 80% of the pixels in every example of digits that you give me. The method still works. The reason it still works is that it is based on decomposing characteristic functions of 3 pixels. So I only have to find enough examples of those 3 pixels across my entire collection of images.
Okay.
And if I have enough examples of those 3 pixels, I can estimate the characteristic function of those 3 pixels, and then I jointly decompose many such little characteristic tensors and figure out the joint density of all. So that's actually a fundamental advantage of the method, that it can work with a lot of missing data in the training data and the testing data, right? None of the other methods, right? You take neural networks, right? Neural networks cannot train with incomplete inputs. So that's a fundamental advantage of the method.
I see.
One of the reasons I'm excited about it.
So that sounds good.
Can I ask something?
Yeah, sure.
Yeah, Yorgo.
That was a question that there is an echo.
I'm sorry, Yorgo, let me reduce my audio. Go on.
Thank you very much, Nikos. I enjoyed the link with Tensors.
And with Fourier.
Yeah, Fourier, yeah. I have another explanation why it works. There must be some people that have their mic on, and that creates an echo.
How?
Okay. Now, you made the statement about VAE, and I typed that as a question. And why do you say that VAE and GANs are not as good? Because this is your competing alternative. Because you said that VAEs produce data, additional data. That's great. Then proceed. Use your favorable PDF estimator. So it's not bad. I mean, as a matter of fact, for inference tasks, you need the posterior. And this is precisely what VAEs are producing, right? In addition to everything else, they produce performance analysis because they give you also the variance.
You know, VAE is one way. Basically, what you're doing is you are modeling, and we have, let's say, VAE extensions of our work, right? But what you're doing in VAE, you are assuming a Gaussian distribution, right?
Not necessarily.
I mean, that's the predominant, at least, flavor, right? You're assuming a certain distribution in the hidden layer, right? And then you map it to another distribution. Do they have any identifiability guarantees? Can they claim that they can get the correct distribution under certain conditions?
I don't think they claim that.
We can, though. We can claim that if indeed, right, the the density is smooth, right? And we pick K appropriately, and it is low rank approximable in the Fourier domain, I can, prove identifiability because of the tensors, right?
That's not as important with a low rank, because a low rank is an approximate model anyways.
It is, but it's a good approximate model. That's what I'm trying to show you through these examples, right? It is an approximate model, of course. Every model is an approximate model. Every model is an approximate model. But what I'm trying to say is, they make an assumption that in the hidden layer, right, there is a certain distribution. And then they take that distribution and map it, right, to make it, simulate the distribution of interest, right? But
yeah, that is correct. It's a brilliant idea, actually.
It is, it is. It works very well. And actually, we can take advantage of it too.
And also the variational approach reminds me a lot, or could be related to your low rank approximation, because this variational density must be a simple density, right? So it should be in the elbow approximation, it should be respecting this independence, what you also take advantage of, right?
Mine is not independent. Mine is conditional independent. There's a big difference. But I think it has to be simple is a wish. Nobody can, my problem with variational autoencoder and other neural approaches is that they don't start from a principled approximation. They say, okay, I will start from this. I will assume this is, let's say, Gaussian, right? And then I will map it and I will try to make it look like what I want it to look like, right? But who tells you that you can do that? Right? A priori, you cannot tell. What I'm telling you here is that if it is compactly supported and if, right, it is continuously differentiable up to a certain order, right? Then I can truncate, I have controllable error, right? And if, and now that's an assumption, I can approximate the characteristic tensor with low rank, right? That's it. Then I can prove all sorts of nice things about it.
They have a principled approach. They find the model which is closest in the KL divergence criterion sense, right? So they it's not that they're ad hoc, right? And the latent variable can have multiple Gaussians, or it can be a mixture of Gaussians as well.
It can, but all of these, so at the end of the day, it is a matter of, as I said, all models are wrong, some models are useful. Clearly, the variational autoencoders are useful.
I think so.
I think, obviously, right? But I think, having a more sort of principled point of view, right? Coming from rank and characteristic functions, right? Something that is a little bit less black box, or, to me, it is a more appealing, let's say, approach. By the way, we have looked at extensions using also variational autoencoders. So you will see some of that coming up. And I think it is, in fact, the methods can be combined naturally in a certain way.
Thank you.
Thank you, Yorgo.
Okay, so I guess it's actually in the interest of time, I think it's time to wrap up. So let's please join me to thank Professor Sidiropoulos for this wonderful talk, and thanks for attending today's seminar as well.
Thank you, folks. Thank you for the invitation. It is good to be with all these friends, and special thanks to Joachim and all these people who haven't slept.
Yeah. Oh, by the way, we're going to send you. So for those questions that has not been answered in the chat box, so we are going to email those to Professor Sidiropoulos, and so he will answer those, or maybe you can email him again to remind about the questions.
That would be great.
Yeah. All right. So thanks.
Yeah, folks, just one more announcement is that we will be having another seminar next week, the same time. Our next speaker is Professor Aldo Scuteri from the Purdue University. So next topic is statistical learning over network, right? So it's distributed optimization and the statistical learning, the combination of the two.
And distributed optimization.
So I look forward to seeing all of you next week. Thank you.
So
Thank you, guys.